Welcome back, everyone, and we're here for another lesson, and again we're continuing with ray intersections. In the previous video we were talking about axis aligned bounding boxes. Today we're now going to deal with oriented bounding boxes. A lot of what we did with bounding boxes in the previous video can be reapplied here. It's just we have to take actually a couple steps. The difference between the two is that here's a good image I found on image search. Here you can see that the object itself is rotated, but the bounding box is not. So an axis aligned bounding box does not rotate. It stays aligned to the axis. Oriented bounding boxes rotate along with the object they're attached to. Just like this example, the box is rotated. So it's the same idea for both objects, but you take extra steps needed to actually do the math for this one. And it's slightly different, but it's the same idea and the same steps. So we're going to have this example, and we're going to have our bounding box rotated in all three axes. So this way you can make sure that everything works just fine. So if we go back to the code, so everything's the same. We're still using our bounding box from the previous video. And now the only difference is that we're going to set its new position, and we're going to set 3 different rotations on it. So every single axis is going to be changed. All right. And then on our on-camera thing, we're going to do a test. And then here we go. We're going to step through this test. Now, the first thing you have to do is figure out the box's orientation. When the box is oriented to the axis, we know its direction. This is like the default direction for everything you create in OpenGL, in WebGL, without any rotation. So if you would add no rotation for the most part, this is usually the direction that everything's kind of built at. It maybe not true, but if you're building everything forward looking, like if the quad's built forward looking instead of like on the floor, this would be its forward direction. It would be 0, 0, 1. So it depends on how you build it. Most often, that's the real direction. It's all based on normals, really. So in the AABB box, we know what our direction is. We don't need to calculate it. We need to figure it out. So for the OBB, we need to figure that out because we need to clamp everything based on its axis. So to find out its directions, you have 2 ways to go about it. In Fungi, we have all our renderables, or actually all our transform objects, have a local and world matrix. So with our local and world matrix all available, we can actually pull the data out of the matrix and call it a day. If you do not have that already pre-built, but if let's say you can then calculate its there's 2 things you can do really if you don't have that world matrix or local matrix type of thing set up in your system. What you can do is take your rotation values and create a rotation matrix out of it, then multiply these values to the rotation matrix. Basically taking the forward direction and rotating it, and it'll give you your new actual forward direction based on the rotation of your object. Same thing is true if you have quaternion. If you use quaternions for rotations instead of matrices, just multiply the quaternion on these directions, and you automatically get the direction that your object's actually looking at. So those are like your basically, like, I guess, 3 options. If you have a world matrix thing set up, you can pull it right out. If you're using some type of just rotation values, you can make a rotation matrix out of it. Or if you're using quaternions, use a quaternions and multiply the standard rotations. And depending on the object too, if you're creating like a plane on a floor, its forward direction, I guess, could be the up direction. You know, it depends. It's a point of view, basically. It's, you know. So let's see. And I found a good image that illustrates it a little bit. So here's a 4x4 matrix. And, you know, here's every column kind of represents its, it actually contains its rotation value. So if you were to take 0, 1, 2 and make it a vector, that is your left axis direction. Or actually, it's right. It really depends on your perspective. In OpenGL, forward is facing toward the camera. So it looks like it's a left direction, but sometimes when we look at things, we look at the opposite way, where forward is seen negative, and by just rotation in general, this X becomes kind of right direction. It's a perspective thing. But I guess for OpenGL, if you want to keep everything in a positive direction, forward is coming toward the camera, and X positive is going left. A lot of code like Unity, they say right, but that's because you're orienting yourself as a person staring at the camera through the camera. So forward is negative and right is negative. So yeah, you just get the values out, and that's what I'm doing exactly here. 0, 1, 2, 4, 5, 6, 8, 9, 5. Create a new vec3. And just create our values. And then we can just output it. So if we go over here, let's shoot a right through, and there's our axis. Green is forward, red is left or right, whatever you want to call it. I guess, like I said, it depends on orientation. So it's the left, and you have up, and it's perfectly aligned to the cube that's rotated. So now that we determined our axis based on the rotation of this object, the next thing we need to do is figure out the distance between the center of our cube and the start of our array, because it's important, because that's going to help us project a couple of things. So if I'm going to shoot a ray through here, probably best wrong direction. There we go. Probably hard to see. So that gray line is the next thing we calculate. It's just the distance between the start of our array to the center of our bounding box. Then the rest is similar to what we did for axis aligned bounding boxes. We do everything based on a single dimension type of thing, but the math is just slightly different. This is the length of the right axis. It's a normalized value by the delta, the length. So we're taking that length and then this length, we add the two and divide, basically creating our projection, just like we did in the previous video. So I don't really need to explain this again. If you watch the previous video about bounding axis aligned bounding boxes, we're doing the exact same thing, but the math is just slightly different. And the first thing we have to define is the axis. So now that the axis has been defined, we have to use those axis values in the math, where before all we had to do was just use all the x values and all the y values and things like that. But now, because of that, we need to actually start doing dot products, and then we can use our axis value for our up and down bounds. And just like I said in the previous, we're trying to find the minimum and the maximum. And then it's like the same steps. Try to find out if max is greater, or if min. Oh yeah, then we're going to save everything to the t max. That's what we're doing here. But it's the same. It's right. I think the next one. Do we do that? T less than max. Oh, okay. So yeah, we're going to do the same thing for the y-axis. It's like we're trying to get the maximus, the greatest min, and the smallest max. It's the same thing. Greatest min, smallest max. Like right here, there's no big deal. So I'm just trying to find min and max. If min is less than max, then min goes to min, max goes to max. Else, if max is actually less than min, max becomes the T min and min becomes the T max. And then we have an extra if statement, which kind of creates, it's based on like some type of parallel intersection, which means there's no intersection at all. So it's just some quick check one tutorial had to use for, just more optimization, just to make, if you're checking this access, but for some reason this happens, exit out. That means you're done. He's like, don't save yourself time from actually going through. So, like I said, this is mostly the exact same thing. That now we're just applying our direction values to the equations. So refresh. Let's see if I do the x-axis. And just like in the previous video, if we're shooting our ray through the axis, it binds the t value between the min and max of the axis. But if I decide to shoot this through a different axis, it's still bound. Let's say that's the z-axis, so which doesn't look like it's bound at all. But the idea is that you need to actually kind of go through all the steps or all the axes and find the smallest possible one. And actually, this is the z-test anyway, so it is still bound. I'm sorry, even though it's going through the z-axis, the ray is going through the z-axis, but the x-test is still bound to the ax position. It's just hard to tell because of the projection matrix, but it's still bound to the left and right min and max. So, and then it's like saying it's the same thing for every single axis. The code just repeats. Like I say, the only difference is that once we do x and we go to y, we then try to find, like, again, the greatest min and the smallest max. That's why we have min here, but we're then doing math.max, trying to find out the difference between the two. If t, which one is the greatest? The t min that we have currently, or the new min that we calculated from the y-axis? And everything else stays the same, and except the only difference is we're doing the min and max of the y. And the exact same thing applies here. And another thing is, it's the up direction. So we're going to do the dot products using the up direction and the y. And if when we do z, we do the forward direction and then with the z values. So if we click save, and you got the same bound values testing as well. So if we click refresh, then we shoot everything through the array. Then we'll see everything. Trying to think what colors are which. Z is green. Okay, so that's why. So we'll shoot the ray through the z-axis, and the green the z-test is what gives us the best values. Excuse me, for it. So if I were to shoot through the x-axis, the x-axis test will be the one that gives us the best values. And if we're going to do through the up and through the y-axis, same thing. And just like last time, let me do a refresh. If you shoot a ray right through all three axes, then you get to see that min and max thing going on. So I want you to get it just right. Let's shoot right through the center. There you go. So there you go. There. So you have an array. That's x, that's z, and that's y, I believe. Yeah, y, because that's the y-axis. And so those are the three tests. We get to see the three values in the three positions, or the three t values, the three t min values that we get when we do all the axis tests. Oops. And just like I said in the previous video, we want the maximum min. So if this is the closest, second closest, and third closest, this is really the maximum min value. And that's the one that's really touching the cube. And that's like the perfect spot. So you just really just travel, you just test every single axis and trying to find the greatest min. And the same thing is true for the max. It's right there. And you can start to see green because based on this test, green and red are very close together, but blue is the right one. It's the one that really touches the cube just perfectly. That's just the right spot on this ray to for intersection. Whoop, let's go. And that is really that's it for object or oriented bounding boxes. It's like I said, it's the same thing, except you need to calculate its new directions and then use those in the equations. And you got an extra test here and there because of this weird orientation thing going on. And just like last time, we're going to go and optimize this because this is kind of silly. It's a lot of duplication. So I'm going to close this up. I'm going to comment this out. And we're going to do this. So first step, like especially for fungi, we're going to make sure that our matrix stuff is updated. Then we're going to call our function. Is it, in the OBB? We're going to pass in our box. We're going to pass in our array. And if it's successful, we're going to create the point on the array. If not, we're just going to say no intersection at all. So, and this is the equation. This is the whole thing. There's some comments like figuring out the ray directions should be something that's done outside of this function. Like I said, this is not perfectly optimized. This is really for more prototyping. Like I said in the previous lesson, the best idea is to create a ray object that holds the direction, the start, the end, maybe the inverse of direction. So this way you can use certain tricks. Like the tricks here, you can be applied here. Well, no, not in this instance, because this is dim length. Like one trick was to try to replace divisions with multiplications by using the inverse value, and you can do that here. You can do one division and then 2 multiplications. I'm not sure if that's really very optimized because I probably 2 divisions probably equal one division anyway. So I'm wasting an extra variable to store that result. So that's probably not the most optimized way of doing it. So in this instance, I didn't bother doing that trick because I just think it isn't really that useful in this instance. If I'm just doing 2 divisions, it's no point in doing replacing 2 divisions with 2 multiplications and 1 division. If I had maybe, if I was doing 3 things based on the exact same value, then I'll probably do 1 division and then 3 multiplications. But since you need to calculate this for every instance of this call, because every box is different, you can't do that little division multiplication replacement. So, but you should really have to calculate the ray direction in one place and not during every time you're doing an OBB test. So, we calculate the distance. We just save an alias to our world matrix. But don't forget, if you don't have this, you have to calculate it based on what type of rotation that you're using for your application, be it a rotation matrix or quaternion. Euler. If you have Euler values, you got to convert the Euler values into a rotation matrix or a quaternion, and then use that to multiply your 3 directions. And yeah, we got our t values. You put 0 and a very large number for max because we're looking for minimum of the t max. So put a very big number in there is good enough, and then just all the other variables that we're using. And the way I'm doing this is that I'm trying to loop through all 4 axes, and since I have a matrix, so I'm going to go through 3 different axes. I'm going through 0, 1, 2. and I can access our access or access the axis. That sounds weird when you say it. So bounds 0 and 1 is in our bounding box object. So that has the vmin and then the vmax, and we can access our XYZ components through XYZ or through an array index. So I is really going through 0, 1, and 2, which is XYZ. So that's why I'm looping through here. So this way, once I loop through, I can get XYZ for this equation. But at the same time, by using I times 4, I'm able to get the location of our directions. So if we're on 0, I can say 0 times 4 equals 0. That's the first point, which is right. And then p plus 1 equals 1, p plus equals 2. If p is 0, I can get 0, 1, 2, which is the right direction. In the instance that I is 1 times is 4, so 4, 5, 6, and so on and so forth. So with a little trick and a little bit of math, I'm able to access my world matrix and my bounding min and max within one simple loop, and by using these index tricks. So yeah, if you just order everything in just the right way, you can really play around with some trickery, and then everything stays the same. And I just noticed that there's a bug in this function. It's not Z. It should be I. That's a boo-boo. I gotta fix that. So yes. Because to find this parallel trick, it's very hard to get the array just in the right spot or something. So yeah, so it works, but this was testing for Z only. So there's a bug that I noticed and fixed. So it's I, and that's it. And if we go to save and then go to here, and you see there's our point of intersection. So we just like the last time, we can go through every single side of the cube, and we can test to see if it hits, and it hits just fine. It's right at the bottom, and shoot it back up, and there it is, right through there. Go through there, and why not? We do that little corner test. Try to get that corner just right, so we can shoot right through it. And it knows that's the top corner. That's the best spot. There it is. Now we have our bounding box rotated, and we can still find the intersection of array for it. It just takes a little bit extra work, a little bit more math. Like I said in the previous video, ideally you would normally, if you have a lot of boxes, like you're scanning through the scene, you should probably do AABB testing first on all of them, and then based on success, and Vita drivers updated, awesome. And when you have that success, then you do the secondary test, which in this case would be the orientation. So this way you can get the right spot of it. Kind of like I said, this video, like you test this one first, then you test exactly where in the bounding box it actually got hit based on rotation. So ideally you might want to do two type of functions. One that just gives you a true or false value for AAB. So this is without actually going through the steps of calculating actual intersection points. So this way you're not wasting your time, because if you're using AAB just to verify that the rate goes through it, and then you do a secondary test for actual intersection, then you have the AABB that kind of returns the t value or the intersection point, whichever you prefer. So that would be like one thing to do, is just write an ABB function that just returns true or false, not intersection, not the t value, just did it hit it somewhere. If it got hit somewhere, perfect. Like if t min and t max, if any one of those are greater than 0, then you're golden. I think that's about it. So yeah. next video, we're going to deal with spheres, then capsules, then terrains. Terrain's going to be tricky, and so is capsules. Capsules and terrains are going to be the trickiest thing to really learn on how to do intersections. But spheres should be similar, simple-ish. So, see you guys at the next lesson. I hope you're enjoying yourself. This is, like I said, like the bounding boxes are the bread and butter of interaction. Especially when you're dealing with mouses and you're trying to find something that you clicked on the screen. For three-dimensional stuff, the boxes and spheres are really going to be your bread and butter. Mostly the cubes are going to be your big thing. But spheres are going to also be kind of big. It depends on the object that you're doing. Yeah, so that's it. Like and subscribe. See you guys at the next lesson.